Okay, so hello and welcome to this video. In this video, I'm going to implement the communication protocol that I'll be using for the CubeSat. So I've not recorded a video for some weeks, but I'm gonna try fast track the progress. And without much further ado, I'm just gonna show you what we will be implementing in this video. So I think I have a video that I have already explained how the communication telemetry space protocol works, PDU, the protocol data unit, and I think I have explained all of these paths, what they mean and why they are there and where they are going to be used. Right, so this is the image that we are going to be implementing. If you've not checked out that video, maybe to better understand this implementation, it's better you check out what is CCSDS telemetry protocol, right? And yeah, so just a quick recap. This is our packet. This right here is our packet. It has a transfer frame primary header, transfer frame secondary header, and transfer frame data field. This is where we'll be packing our data with, a given number of bytes. Operational control field, which is optional, and frame error, right? So these parts are broken down into specific parts, and I will be explaining each part as we go. So just to say that in this single video, I know that we won't be able to implement all of this in a single go, rather in one go, but yeah, I'll try to get much far as I can, rather as far as I can without making the video too long. All right, cool. So let's start, and yeah, so I'll just put this to the side so I can be referring to it every once in a while. And you can see I have created a folder here that is written. It's called the CCSDS C implementation. So basically, this is not coupled to the embedded part. It is just a basic bare C to validate this implementation first before we integrate it into the embedded into the firmware, right? So we have the C and the header file. So I'm just gonna rename this to telemetry, so TM, and it's also the other one to TM, right? So this is CCSDS telemetry. Right, cool. So obviously I'm in the header file, and the first thing I'm gonna do is define header guards. So rather just a brief description of this file is that this file declares the headers for CSDS TM protocol. Cool. So if not defined, let me put this to the side like that. Not defined what was the name of this file is CCSDS TM. Forgot something H. Define CSDS TM H and if, right? So here, first thing I need to define is these variables. So these lengths of the bytes, I need to have maximum lengths of these bytes. So what I'm gonna do is just put that to the side like that. Put that. Where do I close this? Yeah, like that. Because it's the side. Cool. So transfer frame primary header, right? So let me just comment that and say this is header. We'll define this as we go. The name is byte sizes. Let me just call it that. And here I'll say transfer to define transfer frame primary header primary header max. It's gonna be 6, right? Then we wanna define transfer frame. Just copy this one. I'll copy this, put it here. But now this is gonna be secondary. Header max to that. Then we wanna define transfer frame data field. So one thing I have not defined is how big is going to be, how big is my data going to be. So for now, let's start with 1024 bytes max. That's a lot of data. That's 1 KB of data. And if we can't handle this in transmission, what I intend to do is set it in chunks and then recombine it at the receiving end, which is going basically is going to be a LoRa protocol. For now, it's going to be a LoRa receiver. So we can set it in chunks and then calculate the checksum at the receiving end and do it. Reconstruct it at the receiving end. But for testing, 1024 is enough. It's 1 KB of telemetry. That's a lot of data. Yeah, so the next thing is we define the operational control field. This is optional. And then the frame error control field. I'm gonna need the frame error control field because I think I need to calculate the checksum. Yes, I need the checksum. So I need that. Operational control field, what is in that? It's just not present. I'm not going to be using it, so I'll leave that out. And then I'll say frame error. Let me just say transfer frame error field. Error checksum. Let me call it checksum. The checksum makes more sense. And what's the length of that? That's 2 bytes. So it's 2. Right? Alright, so next thing is we want to define the primary header, right? Oops. The primary header. The primary header is made up of these parts. Transfer frame primary header has a master channel ID. All these settings, rather data. So next is what we call the primary transfer frame primary header. This part. Cool. So its length is 6 bytes here, and the first 2 bits are a master channel ID. So you realize that we have gone from bytes to bits, so we need to go down to handling bits. And how I'm gonna use that, I'm gonna do a masking, right? Bit masking. So first thing we define is a transfer. Let me say this transfer frame primary header, TFPH, right? Version number. So those are 2 bits. How do you do that? You shift 1 twice, right? To the left. Let's confirm that. So confirming that, you say 1, bit shift, logical shift, of course. Arithmetic shift by 2. What does it give you? No. Where's my head, man? I want that, right? I want that. So this is 0011. The other way to do it without having a calculation or a shifting problem is to just define it as a decimal or as a hex, right? Or a binary. So for that, this is the LSB right here. See, this is the LSB. It means I'm gonna say this is 0x 0x what? I want it to be 8-bit, so 0x03, oops, 0x03. We can optimize this later, but for now let's work with this. Then we say define tfph spacecraft ID, right? That's gonna be 10 bits. So 10 bits, we are creating a mask, so that you can be able to extract the specific information encoded in these bit positions, right? So 10 bits means again I use this handy tool to do that. These are 8 bits, 9, 10, like that. So this is 8, so this is 0x3ff, this is 0x3ff, right? So starting from the LSB, next thing is we define how we define what to channel ID. I don't think I'll need this. I don't need this operational control flag. Master channel. I might need them. Let me just be conclusive. If I need them, I'll just use them. But let me say transfer frame, packet header, protocol header, primary header, virtual channel ID mask, right? That is 3 bits, right? So 3 bits means we set all of this. We set that. We remain with 0x07. 0x07. I think I should put on some background music at this point. TPFH, virtual channel ID mask. Operational control flag. Operational control flag. This is 0x. This is 1 bit, 01. So it's just 1. All of these are masks. I don't think, okay, mask, sure. Let me disable the minimap. Right, so we define, this is 1 bit. Okay, just thinking, but we will be able to extract that data later. TFPH what? Master channel frame count mask 0x 8 bits on. So the mask is going to be 8 bits. That's FFF. Let me just confirm to be conclusive. Yeah, it's FF. FF. So someone might be asking, how are we going to be using this? So if, for example, I have let me say, if I have this part, if I have these bits, right, so these 6 bytes, and I shift, for example, if I want the master channel ID and I shift this whole data packet to the right by this number of bits, which is 6, which is 16 plus 8, 24 plus 8, 32 plus 1, 33 plus 3, 36. If I shift it by 36 and then and it, and it with the master channel ID, right? Or rather the combination of these two. If I and it with that, I should be able to extract the combination of these 12 bits. And then if I take that and AND it with this specific part and this other part, I can be able to extract that specific information from the header, right? For now, that's what I have from the top of my head, which should be sufficient anyway. So that's why we are having these masks. So it's going to be a master of shift and mask, shift and with the mask, shift and with the mask. Which should be able to extract the given information. All right, cool. So I think time is going so fast. Just try to move as fast as I can here. Count mask. I have here virtual master channel frame count, virtual channel frame count. So copy this and paste here. But now here, this is going to be virtual channel frame count. That's 8 bits. The same thing. The last thing is define TPFH, transfer frame data field status, transfer frame data field status, a long word. 16 bits. 16 bits those are 2 bytes. So 2 bytes. That's 0xFFFF. Right. So I'll just say this TFPH. Yeah. Next thing we define now is we go deeper. The third level deeper is to define transfer frame data field status. Right. So see, this is a transfer frame data field status. Right. So transfer frame data field status. Basically, just metadata for transfer frame. It's metadata for this frame, right? So it is 16-bit, and we have what is called the secondary header status, which has a transfer frame secondary header flag, right? Transfer frame. This is a secondary header. This is the primary header. So this is TF. Transfer frame data field status, transfer frame secondary header. So transfer. I just don't want to mix them up. Secondary header status. Just TF. TF what? TFSH. TFSH. Good. Copy that. Bring it down here. I say define. Find that. What are you defining first? You're defining this transfer frame secondary header flag. Transfer frame secondary header. Secondary header flag. Must be of smart. 0x01. Find. Paste that and say synchronization flag. I don't even think that I'm gonna need that sync flag, but we'll see. You can use it. Who knows? Yeah. 0x01. Define at packet order. How is the packet ordered? Right, packet order flag. These are masks actually, so I should just use masks. I mean, I'll use the word mask so that I differentiate. But they are not variables, they are just masks to extract segment line, to extract data from the CCSDS packet protocol. And mind you, we have not even reached the part for data handling. So 2 bits is 0x02, we are still on the metadata of the header itself, first header pointer. So this and say first header pointer, if I remember well, was a pointer basically to where is the start of the packet, right? First header pointer. Let me start here, mask 11 bits. What is that in hexadecimals? In such situations, it's best to use like a binary representation, but I don't want to type zeros and ones a lot. That's 0x7ff, 0x7ff. So I'll just append the word mask to this to these definitions, mask like that. Okay, good. Next is, I think we are done for that part. Oh shit, there is a transfer frame secondary header. Oh, this is secondary header status. Transfer frame secondary header status. Secondary header status. It should be like that. Suppose there is a header down here. Click, and then S. Right. Next is now the header itself. Transfer frame secondary header. Now this is TFSH. That define. What are we defining? Transfer frame secondary header ID. So I don't need this. I need this exact part. Transfer frame secondary header version number. I'll copy that. I don't know. Let's see. Oops. Okay. Here we go to typing again. Copy, paste. I mean, at this point, you can use AI or something to just type for you faster, but where is the joy in programming if you can't feel the strokes of your keyboard, right? Transfer frame secondary header. What version number? Version number, that's 2 bits, 0x02 mask. Someone might ask why I'm using two long words. I mean, two wordy variables or definitions. But I'll tell you this, that it's best to have worded variable names, TFSH, than to have very short frames or rather short words, because the moment you start revising or debugging this code, it will be of great help to have words that actually describe 6 bits, words that describe what exactly that definition stands for, right? So it's best to write them as whole words. This is 6, right? 4 as 3f, 0x3f. All right, define sync as knowledge. Transfer frame secondary header data field, right? So this field right here. Let me just zoom in a little bit. This is the field I'm talking about. Transfer frame secondary header data data field 0x. Oops, how long is that? Was it? I don't know. I do not have up to 64 bytes. That's a lot of bytes. How do we define that? Up to 64 bytes. I mean, 64 bytes is like 64 times. Okay, we don't need to define that. We can say transfer data field max length right? Let's just say this is 64, right? Mask, yeah. All right. So we have those few definitions. There are libraries that have been written for this anyway, but again, where's the joy? You can't try to do it yourself first before referring to what has been done before, unless time is not really on your side. Cool. So let's go to the next thing, which is we have done this. Let's go to this operational control field. Remember, we have skipped data. We'll define the data at the end. Operational control field, which is optional. Am I using it? Let me follow these lines. Not present. Good. Frame error control field. I think I did that definition. Checksum is 2, right? So max, this is okay. Data field, I defined it. Max length, oops, length, like that. Max length, and then max length. What am I doing? Length, yep. Then checksum 2 bytes. Cool. So let me just call it a mask because we need to extract those 16 bits. Are these 16 bits? Yes, 16 bits of the checksum first. Right. All right. So that's that about the definitions. If we discover anything that we need, we just add it there. But yeah, that's good for a start. Now, how are we going to test this actually? Like, how are we going to test it? So let's start with the most obvious thing, data. How are we going to define data? So for my case, I have a lot of telemetry, which I'll discuss in another video. Like you have things to do with the OBC, EPS, communication, protocol, the payload itself, all that is like telemetry. And it has to fit in 1024 byte packet, right? So what I'll do, I'll just add a simulation generation, like a faker, a faker function, right? This let me just say this is brief faker function. Oops, hope you can see that. So let me close that. Faker function generate dummy telemetry. I'll call it a void telemetry generate void. What does it return? What should this return? This should generate, okay, let's say what it should do first. It should generate OBS data, generate EPS data, generate EPS, what else? Comms data. Then we want to generate what? Payload, sorry, payload data. Cool. Now, once we generate that, we want to put it in a buffer, and then we want to transmit, right? So, for example, what data can we get from the OBS, right? Let's start with the most obvious timestamp. This is fake, so it's gonna be like just a few values. Timestamp. Let's what else OBS can you get? What OBS data can you get? Let's say board voltage, right? Board current. I forgot ADCS. Generate ADCS data. Right, board current, board voltage, timestamp, let's say uptime, how long has this satellite or CubeSat been on, and one last thing, there's a lot of things you can give here, but I just want us, there we have the EPROMs, RTCs, hardware watchdogs, whatnot. Let's call it number of resets. Okay, so timestamp. This is most of the time, actually 99% of times is always a unit 32. That means we need include std int here, right? So come down here and say timestamp is going to be a uint 32t OBS timestamp, right? Okay, so OBS timestamp. Something fun that we can do is use the max values for this. So you need 32 max, right? Don't have negative time basically, because that means you'll be going back in time, but are going to travel into the past, which is not possible. Board voltage is going to be a float. Now there are issues that come up with the float sizes and memory usage, but OBS voltage, OBS board voltage. In the actual CubeSat, we realized we'll have 5 volts, 3.3 volts, and 12 volts supplied to the OBS, so this is going to be times 3. This is float. There is no float max, but let's just say it's 3.3 or 3.3 line, right? 3.3 board current. Let's copy this and put it here. Board OBS board current. This is the consumption, right? This is 250.0 0.5 milliamps. Fingers are getting heavy. Uptime is within 32t. OBS uptime. What's gonna be? Let's take it to something like 45 500 seconds. In seconds. Number of resets. This should be as few as possible. So let's just say that it's going to tap out at unit 8. 255 resets. If you have that many, then that means you designed a very bad system. Unit 80 OBS reset. I'll call it reset count is equal to, let's say you have 10 at the point at the moment. Sure. Missing a column there. Generate EPS data. So we'll do the same for this EPS, ADCS, and whatnot. So let's try ADCS and say float OBS ADCS X acceleration float ADCS Y acceleration float ADCS Z acceleration. That's gonna be 6 point. That's a lot of acceleration, but 6.3 is gonna be 0.5. Wait, it means this thing is falling down or what? If this is 6.3, let's make it move to the side. A bit of mechanics, I think, is gonna, like, I don't know. So I think it's just best if we be able to be realistic. I don't know, 3. Assuming y direction is like following the orbit, so should be moving forward, not down or up. But there's a slight atmospheric atmospheric gravitational pull from other for objects that are close to the surface, just in space but close to the atmosphere. So at the end of the day, it's gonna try to come back to Earth. Anyway, that's beside the point. We're gonna do that for the constant payload and the EPS. But for now, we work with this telemetry generate dummy. I realize that I'm in the header file, but I defined a function. So I'm just gonna copy that and then just do this and bring it here. So include CCS, CCSDS right? And because this is like C on the PC, you can say include std. I think we are also going to need string. I don't know, string. We might need some math. We need math really? No, we don't need math. Yeah, we don't have algorithms that are doing math at this point. Good. Right. So this video, I have like 4 minutes left. So what I'm gonna do at this point is make this maintainable and scalable. So by scalable, I mean, you see this whole class or this whole data point, I'm gonna try and make it a class, rather abstract in C, right? This means that I'm going to have rather the reason I'm making it a class is so that I can have like a single instance of the telemetry packet, right? So they belong to different, I can have the same CCSDS packet for different CubeSats or for different versions, right? Because you realize these are just generic functions that will be called, right? So what that means is that yes, I can define these as like generic definitions, but down here, let me now start implementing a class, right? So it says struct, let's use type def, struct CCSDS packet, TM packet, right? Packet CSDS TM packet, right? Down here I define struct is define that how to get copy twice, whatever. So what is this going to have, right? Generally, typically when you're defining classes in C, you need function pointers so that you can be able to implement later on subclasses, right? For example, what I'm thinking is that this is the telemetry protocol, and we might need, there was a TM, telemetry, and telecommands. Yeah. So telecommands should actually just inherit from the parent, which is the TM packet. At this point, what I need is the TM packet. Or I can just have CCDS packet. Actually, it's a good thing that I thought about it that way. And now this is going to have a pointer to itself. Just no, let's just have the functions void create void CCSDS packet create, right? What does it return? I want it to return a pointer to this. So that pointer, right? That's something to do with memory allocation initially, right? And then the next thing is you need to initialize it. So void, just copy this, init, then say void. If you create with dynamic memory allocation, you have to destroy that memory. So we will just say CCDS packet clean up, right? This is a distractor, right? It's a distractor. Good. Now, void, what else do we need? We need this faker telemetry generate dummy faker function. So void that faker telemetry faker. So if you see that I have no idea of what I am doing, it's actually because I have no idea of what I am doing, but I'm just going with the flow, just thinking it as I go. I have some ideas, but yeah, whatever, man. We'll see how it works out. Good. So if we go with this, we are not going to be able to implement subclasses, which means that we need to, okay, to be able to implement subclasses, we need to introduce function pointers, and function pointers are a tricky subject, especially in space implementations. NASA does not recommend usage of function pointers, but whatever, man, just use them for now. Void CCSDS packet init, right? So we want to make this a function pointer that takes nothing, but it's called CCSDS packet. That's the name of that function, right? So I just convert this to just quick function pointers. This is the syntax for function pointers. It's not complicated, it's just that. This is the name of the function. These are the parameters. So if this, for example, this one takes a void, it does not take anything, right? It does not take anything. Good. Right. Init, clean up, create, then we have a faker document, faker function. Okay, so man, the video is long. I don't want to keep it going for long, but here we will just create functions, right? Actually, this init should take what is called the function pointers as arguments themselves, right? As argument, and then assign these pointers to those arguments. So for example, it's supposed to take this signature of the function, right? Doesn't have to have the same name, but packet cleanup, I'll just have a function so that I can be able to differentiate them, right? Like that. And then it takes same thing, like here, void, paste that, then we call it function. So this is a very basic class architecture in C. Then we are gonna take this, the faker. The faker can be anything, right? So after that, function. Where is the function? Right. Wait, where is it? Where is the error with this thing? Oh, this one. Yeah. Just packet cleanup, or duplicate cleanup function. So there's a cleanup function, there was the init, there's the cleanup, there's the, those are enough. We'll add others as we go. So for now, let's just use 2, I think. Yeah, 2 are enough. Then create functions here. All right. After creation of functions, we'll call, no, after creation of functions, we'll call init with the created functions, right? I deleted, did I delete? No, I did not delete it. All right, cool. So, yep, they should be good. Header file. So the first thing that we can create is these creation functions, right? So what does this do? So create CCDS, right? So these allocate memory for the CCSDS packet, right? So it's just a very simple malloc that returns CCS. The reason I'm repeating the CCSDS packet is because this firmware is going to be so big. Rather to have a lot of components that I need to have the subsystems named on first name basis so that I can be able to search the code base way fast. It is a form of indexing, but from how you name your variables and functions. CCSDS packet, let's say pkt is equal to alloc. No, it's got to convert it to, what am I doing? Convert it to this. Other force are conversions for conversion because malloc returns a void. Pointers for malloc. What are we allocating? Size of what? So here we need to calculate to know how big is this. How big is this going to be? Right? How big can it get? This is 664 plus 70 plus n is 1024. 70 plus 1024. Let's check. Clear that. 70 plus 1024 plus 1094 plus 4 plus 1098 plus 2, 2k, 2000 bytes, right? So let's say find max CCS, yes, max packet size. That's 2000. I like to put them in brackets. It's not necessary, but yeah. So CCDS packet size. So we want to allocate those number of bytes. Yeah, there's a lot of work to be done here. Is this actually right? I don't think it is right because size of what is this? This is not a defined thing. This is actually very wrong. We need size of those are bytes times times this. Yeah. But shit, I said I have 4 minutes and it's 4 minutes and it's almost 10 minutes later. I'll just end it here. Malloc is in the std lib, that's why it's having an issue here. So include std lib. Right. I think what I'll do next is implement. For example, if you allocate the memory for this and your struct does not, so CCDS packet will be pointing to a memory that has this 2000 bytes. Okay, yeah. Another way of implementing it is actually having these parts, the flag, the sync flag, packet order as part of the struct. But now that will beat the whole purpose because I want this to be a base class, right? Base class brief. Base class for CSDS protocol. Yeah, anyway, other issues we'll discuss them in the next video. So let me end it there. And this is just a poor man's way of implementing a protocol. This is a very poor man's way of implementing a protocol, but it's not bad. It's good for a start, and we'll be figuring out other things as we go. Right? This needs to be changed and whatnot. Cool. So sure. give it a like or whatever, or subscribe. I don't really mind about that, but yeah, see you next time. I'm out.